I will present a study on materials testing for hydrogen compatibility, basically steels, but we will see other kind of steels as well. I work for Air Liquide in Grenoble area in France. It's Air Liquide Advanced Technologies. It's a specific department of Air Liquide where we produce specific machines for gas. We don't produce the gas, but we produce the machines, like rotating machine, for example, pumps, turbines, and so on, to use hydrogen, helium, oxygen, nitrogen, and so on. Okay. So today I will do some advertising for Air Liquide and then show you how do we test, what's our materials testing methods, how do we choose our materials, and some results of tensile testing. So decarbonizing the planet is in the heart of ADVANCE, which is Air Liquide strategic plan, and where hydrogen plays a key role. And Air Liquide has a great expertise in hydrogen for more than 50 years, an expertise that covers the whole value chain from production to distribution. So if we look into production, for example, we cover electrolysis and also the reforming of methane and ammonia. To give an example, in the project Normandy, the group produces the first and largest low carbon hydrogen for industries in the region. If we talk about distribution, storage and usage of hydrogen, we produce pipelines and also cylinders and tanks, sometimes even on boards, on ships, on boats, or even on airplanes, either in gas state or liquid state. And to finish with the value chain, we also cover the distribution areas using our large liquefiers from Air Liquide, as well as all the equipment for gas-to-gas or liquid-to-gas hydrogen supply chain. So metallic materials are very important in the value chain, of course. Air Liquide has the expertise in metallic materials as well. In the classic services like pipelines, exchangers, and mechanics, we know what kind of metals we should use to avoid failure or safety risks. But in some cases, we have some machines, like it could be rotating machines, for example, that are used in different kinds of gases, and we need to retrofit them for hydrogen. Sometimes we have materials that are not predictable in hydrogen, or less predictable, at least, in hydrogen service. And the main rule for us is to assess the risk of embrittlement, whatever the case, whatever the service, even in liquid hydrogen facilities, because we always have some start and shutdown phases where we have gas. So to do the qualification of materials, we use the main methods and standard tests that are very known. For example, just a few examples, for our cylinders and the tanks, we use the famous ISO standard, the disc burst test, where we have a thin disc and we increase the pressure until it bursts in hydrogen or in helium using different pressure increasing rate. And then we calculate the embrittlement index with the pressure of helium divided by hydrogen. So this is typical for cylinders and the tanks. We also, for whatever else, like components that are in tensile configuration, we can use the famous slow strain rate testing, either in autoclaves or by using the hollow specimen, the newer testing that you already heard about. Today, I will show you results with this kind of testing. I will not go into fracture mechanics. Many other people talked about them, just to say that we do these testing at Air Liquide in gas soon, but we already do it for tens of years in liquid hydrogen at 20 Kelvin in situ, and also in helium, liquid helium at 4 Kelvin for many applications, especially space and other. So if you need any other information about this, just please let me know. So we chose to test lately, very recently, 6 kind of alloys with slow strain tensile test in 2 different kind of conditions, because we have different applications here. One with 120 bars and another with 150 bars at 25 and 60 degrees. We have nickel-based alloy, chromium molybdenum steel alloy, 2 martensitic stainless steels, 1 cast ductile iron, and 1 forged steel. The application and the detailed composition are confidential. So the tests were done in autoclaves with a strain rate of 5×10⁻⁶ in air or nitrogen versus helium and hydrogen. We focused on ductility as usual, so we measured the ratio of elongation in hydrogen versus helium, and also the reduction of area, called RZ here, to assess the loss of ductility due to hydrogen. So if we start with the results, first with the nickel-based alloy, this is very reliable for oil and gas application. We can find it a little bit everywhere, the nickel-based alloy. So we know it could be influenced by hydrogen due to precipitates at grain boundaries with chromium, molybdenum, and the nickel components. Our tests definitely show a huge effect of hydrogen, both at 25 degrees and 60 degrees, and the effect is even more severe at 60 degrees. We have a loss of elongation of more than 50% and the loss of ductility of almost 65%, which could be seen, not good enough, but yeah, in the photos, we can see the crack and also the secondary cracks and the loss of ductility on the specimen. If we go through steels now, the martensitic precipitation hardened martensitic steel. So this is less obvious. We don't have any effect at 25 degrees, 120 bar, but as we increase the temperature to 60 degrees, we have half of the specimens showing a decrease of the ductility, even 42% of loss of elongation. But yeah, we have a huge scattering of the results, which makes it more complicated to conclude. But this was only last week, so more tests will be conducted on this kind of material and also other kinds of tests. The other martensitic stainless steel is a nitrogen doped that is used in precision mechanics. We know that it could be susceptible in specific configuration, but in tensile testing, although slow strain, at 25 or 60 degrees, we don't see any effect of hydrogen. But this alloy is used in dynamic contact fatigue life, so we should do a specific test that is adapted to this configuration. And this is expected for the near future. At least in tensile configuration, there's no effect. Now, if we look into the quenched and tempered low alloy steel with chromium and molybdenum, it's also a little bit disturbing because we don't have any effect at room temperature. And as we increase the temperature only to 60 degrees, although, of course, we have a larger mobility and larger diffusion of hydrogen, we have quite an effect of hydrogen on the ductility and the reduction of area. But the different, I show only 2 examples here to show you the difference. But yeah, we have also some scattering at 60 degrees that should be clarified. Now, we also looked into the cast ductile iron because we have it a lot in many rotating machines and we cannot do without it. We know it's susceptible, but we didn't know how much. So we tested this quite ductile iron, and it revealed that it still has it is slightly sensitive to hydrogen embrittlement. We have a loss of 29% in necking effect and the ductility, which should be considered in the design rules. And now to finish with the ultra high strength forged steel that could be seen in shafts, in cranks, and so on. We always knew that high strength materials could be vulnerable, but we didn't know how much vulnerable. So we tested our materials, and we could see a huge effect of hydrogen on these materials, even at 25 degrees, 150 bars. We have a loss of elongation of 84% average. Of course, these are the average of at least 3 specimens in each condition. So that's it. I covered already the whole thing. We started with slow strain testing to screen the materials. Of course, it's only the first step. So some specimen will be tested also with fracture, toughness, and so on, depending on the configuration. We could already see that there is no obvious effect on mechanical characteristics, but on ductility, we still have a huge effect on nickel-based alloys, especially at 60 degrees. No effect on nitrogen-doped martensitic steel, but we still have some effect on precipitation-hardened stainless steel, chromium molybdenum quenched and tempered steel, especially at 60 degrees, but should be clarified in further tests. So again, the cast ductile iron is sensitive up to 29%. It's something to consider. And we confirm that the very high strength steel is very susceptible to hydrogen. So again, this will be completed with further tests soon. Thank you for listening.